This video deals with asymmetric encryption. That is, how to do encryption, decryption with pair of keys. What one key encrypts, only the other can decrypt. There are not many applications of asymmetric encryption because compared to symmetric encryption, asymmetric encryption is slow. And it requires much longer keys than symmetric encryption. One of these applications is a key exchange protocol where the symmetric key is shared between communicating parties through asymmetric encryption. Asymmetric encryption is terribly slow compared to symmetric encryption. And when I say terribly slow, I mean 1000 times slower. So asymmetric encryption cannot be used to encrypt communications. There are basically two asymmetric encryption systems: RSA encryption, ElGamal encryption. I will present neither of them. Security of both algorithms is based on the difficulty to resolve a mathematical problem. Finding the factors of a large composite number for RSA and computing a discrete logarithm for ElGamal. But I will not deal with this. I will only present their common principles regarding encryption and decryption. Asymmetric encryption, whether it is RSA or ElGamal, uses pair of keys. ElGamal uses the Diffie-Hellman protocol for generating public key-private key pairs. RSA has its own key generation algorithm for generating public key-private key pairs. Size of keys is similar for both ciphers, in the order of at least 2048 bits. ElGamal and RSA differ in the way data are encrypted and decrypted, but both algorithms share the same common principle: what one key encrypts, only the other can decrypt. Let me show you briefly how it works. Suppose Bob wants to send a message to Alice. Bob uses Alice's public key to encrypt the message. Bob sends the message to Alice. Alice decrypts the message with her private key. If Alice needs to reply to Bob, then she will use Bob's public key to encrypt her message. More formally, let us consider a pair of public-private keys. And let us consider an asymmetric cipher. The decryption with the private key of the plain text encrypted with the public key gives back the original plain text. This is what I described in the previous slide. But we have also the decryption with the public key of the plain text encrypted with the private key gives back the original plain text. Okay, that's fine, but is it useful to encrypt some data with a private key, knowing that everybody will be able to decrypt the data using the public key? Yes, it's useful for one important application of asymmetric encryption, namely digital signature. Asymmetric encryption is randomized. That is, the same input will never produce the same ciphertext. Since I will not present ElGamal and RSA, I will not present how these ciphers are randomized. The randomization of these ciphers is of course intended to prevent security problems similar to those related to the electronic codebook mode of operation of block ciphers. Basic asymmetric encryption, as described previously, faces two important conceptual problems. The first is, how can Alice be sure that the message sent by Bob actually comes from Bob? Indeed, anyone can send an encrypted message to Alice, since everyone has Alice's public key. So this is the first conceptual problem of asymmetric encryption. And as we will see later in this course, the solution to that problem relies on the digital signature. The second problem is, how can Bob be sure that the public key he is using to encrypt his message to Alice is actually Alice's public key? This is the second conceptual problem of asymmetric encryption. And as we will see later in this course, the solution to that problem relies on the certificate and public key infrastructure. I already said it, but I repeat it. In practice, asymmetric encryption is not used for encrypting communications because it is too slow. The two major applications of asymmetric encryption are symmetric key exchange as an alternative to the Diffie-Hellman protocol, and the most important one, digital signature. And I will talk about digital signature in a separate video. Let me conclude this video by showing the key exchange protocol using asymmetric encryption as an alternative to the Diffie-Hellman protocol. And by the way, at this point you might feel a little bit lost. So I want to recapitulate a few things. Asymmetric cryptography refers to cryptographic constructions using pair of keys. The Diffie-Hellman protocol is an asymmetric cryptographic protocol since it uses pair of keys. But the Diffie-Hellman protocol does not use asymmetric encryption. Please refer to the video on the Diffie-Hellman protocol and you will get the confirmation that not a single message of this protocol is encrypted. On this slide, I will show you through an animation that we can define a symmetric key exchange protocol by using asymmetric encryption. Bob and Alice need to share a secret key for symmetric encryption. They can use the Diffie-Hellman protocol for generating the secret key, but alternatively, they can also proceed as follows. Bob randomly generates a secret symmetric key. Bob encrypts the symmetric key with Alice's public key by using an asymmetric encryption system like RSA. Bob sends the encrypted symmetric key to Alice. Alice decrypts the symmetric key with her private key. The symmetric key is used for encrypting the communication between Alice and Bob. This video was about asymmetric encryption. I mentioned two asymmetric encryption systems, which are RSA and ELGAMAL. I also presented one of the applications of asymmetric encryption, which is the key exchange protocol, as an alternative to the Diffie-Hellman protocol. Please note that in SSL TLS 1.3, only the Diffie-Hellman key exchange protocol is supported. Key exchange protocol using asymmetric encryption is not supported in this last version of SSL TLS. In fact, the main application of asymmetric encryption is the digital signature that we will see in the next video.